so BJT is bipolar junction transistor. It is another type of transistor where we have previously we have diode topic. Okay, now we have transistor topic. So in this syllabus, the transistor topic cover for BJT, bipolar junction transistor, and the other one is MOSFET transistor. Okay, so first one is BJT. Okay, BJT is bipolar junction transistor. So what will be covered in the chapter, in the part 1 of BJT is the basic operation of BJT, the IV characteristic, as I think same like diode. Okay, you know the IV characteristic and also the transistor's mode of operation and application. The last one is the introduction to the basic amplifier circuit and it has some parameter, the voltage gain, the current gain, and the total impedance at the input and total impedance at the output. Okay. AV means voltage gain. AI means current gain. Okay. So this is the transistors type. Okay, so we have two basic type of transistor. Number one is BJT. Okay, number two is FET, which will be in the next chapter. Okay, so BJT basically it is more complex. Okay, why? BJT has two junction actually. So previously you have P and N junction, but BJT is the combination of dual PN junction. Means in BJT it has two PN junction. Okay, diode has one PN junction, but in BJT it has dual PN junction. Okay, so this has dual polarity as well, where it refers to the holes and electron as carriers. Okay, in BJT, it is used mostly as amplifier and sometimes as a switch in the circuit. Okay, so when it is used as amplifier, it is used to amplify the signal. Okay, when you have input signal with 10 volt, okay, you want to amplify your signal, okay, become with the gain increase, maybe 20 volt, okay, you might want to use BJT as an amplifier. Okay, amplification can make weak signal become better signal. For example, microphone. Okay, it is one of the example of amplification system. Okay, in general, why? Because amplifier provide gain. Okay, where it can the output value is the multiplication of gain and the input value, right? And this is the basic structure of BJT. So for BJT, it has three terminals. Okay, so this is how it looks like. Okay, the symbol. Okay, the symbol for BJT, and BJT has two type actually. So it has so this is the symbol. Okay, one it has the NPN. Okay, and the other one is PNP. Okay, it has two types. So what makes these two different NPN and PNP is the arrow of current. Okay, arrow of current. Okay, so it has three terminal. Okay, collector, base, and emitter. So when it has three terminal, means it has three currents. Okay, that's why I said BJT is more complicated. Where diode you only have one current flow. Okay, it's either forward bias or reverse bias, ID. But in BJT you have three currents. Okay, base current, okay, collector current, and emitter current. Okay, bipolar, since the conduction current is due to the majority and minority current. Okay, so this is how it looks like, the symbol. So, but this is the basic structure inside your BJT. Okay, so you have base, collector, and emitter. At collector, so collector is made up of the N type. Okay, and base is made up of P type, and emitter is made up of N type, as you can see here. So this is for the case of NPN. Okay, for the case of NPN, the collector is N, the base is P, the emitter is N. Okay, however, for the PNP type, okay, where it has different direction of current, so the collector is made of P type, base N type, and emitter P type. Okay, so this is how differentiate between the NPN type and PNP type. Okay, so again, okay, for NPN, it has two N regions separated by P region. So this P region is actually very lightly doped. Okay. Okay, so for this case, the N region is lightly doped. So when I said lightly doped, why? As you can see, P region here is very thin layer compared to the N region. Okay, in NPN junction. However, in the PNP junction, the N region is very small or lightly doped compared to the PNP regions. Okay, so doping level. Okay, BJT, now we are looking at the type of NPN. All right, so BJT is constructed of three layers. Okay, so it is sandwiched between alternating dope semiconductor material. So in the emitter, okay, emitter is heavily doped N type, and the base is lightly doped P type, and at the collector is heavily doped with N type. Okay, so here, that's why I said it has a dual PN junction. Okay, let's take a look on the NPN here. So this is NPN. Okay, therefore, you have two diode connect together. Okay, so in here, you know that you have this is P, this is N, and this is N. So you have, it's like two PN junction connect together. So you have one side here PN junction and the other side here PN junction. So it is quite complicated, but then you can actually get the current as well. Okay, so for the NPN, so current from the collector is the IC, collector current, okay? And then current at the base, we call it as a IB, base current, and current going out from emitter is IE, which is emitter current. And each of the junction also has voltage drop. Okay, from collector to emitter, it has VCE. From base to emitter, it has VBE, and from base to collector, it has VBC. Okay, so that's how it defines. Okay, it has several currents and also several voltage drop across the junction. All right, so this is the basic structure. So you know that in here, okay, base is very thin. Okay, therefore it has very small majority carrier, means very small number of holes here. But collector and emitter has large number of majority carrier, which is electrons, okay, at collector and also at emitter. Okay, but collector is made up a bit wider compared to the emitter. Okay, so the terms here, emitter will emit current, okay, will emit charge, okay, and collector will collect charge. Okay, so base is usually works as a gate, okay, to control whether current can flow through it or cannot. Okay, that's how you do it. Okay, so it's either so current. So in here you have IC. Okay, at here you have IE. Okay, here you have base current. So usually base will behave as a gate. Okay, it's either to allow current IC to pass through or not to the IE. Okay. So vice versa for the PNP. So PNP at the center here, it has a very thin layer of N-type material. Okay. All right. Okay, so this is how the structure look like. Okay, from base to emitter junction. Okay, from base to emitter here. Okay, the PN junction joining base region and emitter region. Okay, from base to collector junction, the PN junction joining between base region and collector region. quite boring for the first part, but that's fine. Okay, so transistor operation, okay, it has mode of operation, I must say. Okay, so in your diode, you see that the diode in active region when it drop at the Q point. So Q point is where your diode is at active region. So that is your Q point. Okay, for your BJT as well, you have biasing mode. Okay, not only active region, it also have saturation region, okay, inverted region, and also cut off region. Okay, in this case, okay, the desired mode of operation, if you want your BJT to behave as active mode, active region, okay, you must connect it correctly. Okay, for example, your diode, okay, you want to make your diode become forward bias, okay, you for example, you have diode. Okay, if you want to make your diode forward bias, you must connect this side to positive terminal, right? And the other side to negative terminal. Am I right? Okay, so as your BJT. Okay, your BJT, since you have two junction, okay, from base to emitter here, okay, from base to emitter and collector to the base to collector. So this must be connect properly. Okay, it's either this one base positive or it's either this one negative. So it depends. Okay, so how it depends is here. So it has three mode of operation. Okay, if you want to make it as active, okay, active. Okay, you have to connect between base to emitter forward bias, okay, and base to collector reverse bias. Okay, if you want to make it saturation, means that your BJT is on. Okay, both junction must be connect with forward bias. Okay, so inverted means that rarely being used, okay, but then it is actually off lah. Your transistor is off. Okay, cut off is when you want to turn off your transistor. Okay, usually saturation and cut off is where you make your BJT as a switch. Okay, switch is either on or off. It's either become 1 or 0, right? So cut off, you have to connect the two junction is reverse bias. Okay, we'll take a look on the example. So this one, for your saturation region, it will be, we consider it is on. Okay. Okay, and then active is when you want to make your BJT become amplifier. Okay, so inverted is off, cut off is also off. So usually these two will behave as a on switch. This will behave like a off switch. Okay, and active mode is when you want to make your BJT become amplifier. Okay, so this is what I mean by the forward active. So forward active means that BE junction here, your base to emitter junction, this one, forward bias, collector to base junction, reverse bias. So let's take a look. Okay, so you have here base, collector, emitter. Okay, let's take a look at these two first, base to emitter. So base to emitter must be forward bias. Okay, forward bias. We know that this is NPN. Okay, so you have NPN. So this is base and then collector, emitter. So NPN, this is N, this is P, this is N. To make it forward bias, P side, which is at the base. Okay, you know from the diode, to make your diode forward bias. So this is P side, this is N side. So P side must be positive, N side must be negative in order to make the connection become forward bias. There you go. Same goes to BJT. Okay, same goes to BJT. Your P side here means the base. At the base must be positive. okay, the emitter here negative. All right. From collector to emitter positive and emitter of course negative. So that's how you make it become forward bias, okay, and reverse bias, okay, this is how you make it. So this is positive at the base, so this is for PNP, this is for NPN, vice versa, okay. So forward bias, okay, for forward bias, this junction base to emitter, it will narrow, or the depletion region become narrower, okay, therefore it will allow current to pass through, okay. For the reverse bias, this one become reverse bias, will widen the depletion region. All right. So for NPN, the base to collector junction is reverse bias when the collector is made more positive than the base. Okay, what is more important is at this side. Okay, so let's take a look how it behaves. So this is actually the example for the NPN. So how actually electron diffuse when voltage is connected. So as you can see, so this is base made of p type. Okay, this is electron. Yeah, emitter, which is made of n-type. So you have the majority carrier here is electrons. Okay. At the base here, you have majority carrier here holes. Okay. Now, electrons, now you connect with the positive forward bias. This is positive. Okay, this is negative. Okay, therefore the electrons here, okay, the electron from the majority carrier n type here will be attracted to the positive plate here. Okay, same happen during PN junction. Okay, same concept actually. Okay, and also this the PN junction here will become narrower. Okay, so this is P, this is N, so this will become narrower and it will allow current to pass through. Okay, how about this region? From base to emitter, it has plus as well. Therefore, electrons from this collector inside will be attracted to this positive plate. And this one will become widen, okay, widen the depletion region. So that's why I said BJT has two PN junction when it is connected to the forward bias or forward active mode. Okay, one, this region will become, depletion region becomes narrower and this depletion region will become wider. Okay, so this is vice versa for the PNP. Okay, so the current, okay, the transistor current exists or occurred here where you have IB. Okay, so you have, it's like this. Okay, so you have current IB and you have current IC and you have current IE. So it's like point at the center here. If you apply KVL, okay, total current in is equal to total current out. So this is current out equal to the total current in. Okay, so current out from this node is IE. So current into this node is IB plus IC. So you will be using this equivalent current. Okay, so IB in this case, usually IB will be in microampere. Okay, very small. And IC, okay, is and IE also will be in milliampere. So we say that current here, IB is very small because it is microampere and IC and IE is in milliampere. All right, so there will be three currents, okay, base current, emitter current, and collector current. And also there will be three voltage, okay, base to emitter voltage, okay, means that junction voltage. So you have this voltage and you also have this voltage, okay. The only important voltage is these two, VBE and VCE, okay. But currents are all important where you need to know lah, okay. So this is the collector current. So collector current is made of the minority current, minority carrier, and also majority carrier. So the only thing that you should know is this one. Okay, so alpha is actually another parameter. We call it as, so alpha in here from the simplification here. So alpha is actually equal to the IC over IE. Okay, for a good amplifier, a good BJT, alpha is usually approximately equal to 1. Okay, by this reason, we can assume that IC is approximately equal to IE. Okay, why? Because both collector and emitter is doped with the same concentration, and base is usually very, very small, and therefore we can assume that IC equal to IE. Okay, from this question, if let's say we neglect IB, okay, because IB is microampere, so IC is approximately equal to IE. All right, so other parameter is beta. Okay, when you want to make your BJT, usually BJT has beta value, okay, because most of the time BJT is used as an amplifier. So beta value is actually a gain value, gain factor. It is a gain factor. So beta value usually very large. It is more than 100 or 200. So everything output from the BJT will be multiplied to the beta value in order, it is like a gain function lah. It's a gain factor. Okay, so beta, so from this equation, so beta is equal to IC over IB. Okay, so if you given IB and also beta, you can straight away calculate the IC. Okay, let's take a look on the example later. Okay, so this is the alpha beta relationship. Okay, you know from this one, so this is the first one, alpha is equal to IC over IE, and the second one, the gain factor beta, IC over IB. So if you rearrange the equation, okay, this part is important. Okay, right? So this part is important. If you rearrange the equation, okay, you know that IE is equal to IC over alpha, this one, and we remain IC. And then IB is actually IC over beta. Okay, if you rearrange this equation, you will get that alpha is equal to beta over 1, or beta is equal to alpha over 1 minus alpha. So this is actually the rearranging the equation basically. Okay, and if you rearrange this part, okay, you will get that IE is equal to beta plus 1 IV. Okay, so this formula, okay, all 1, 2, 3, 4, you need to memorize this. Okay, in BJT, okay, from now on you will be using this 3 formula actually, 1, 2, 3. Okay, you will be using this. Okay, transistor configuration. There are 3 types of transistor configuration. Okay, now, so you have learned so far. So this is your base, collector, emitter. For example, we are taking the NPN type. Okay. Okay, so you have 3 terminals, right? Okay, so there are also type of configuration. Okay, we have common base, common emitter, common collector. Common means, okay, the base, common means the ground. Okay, the ground. Okay, when it say common base, means that the base is grounded. When it says common emitter, means emitter is ground. When it says common collector, is collector's ground. But then in your syllabus, we only cover common emitter. So only this part, okay, where emitter now will be grounded. Okay, for example, if you have, of course, it's each junction have resistors, so emitter is grounded. So this one will be covered in your syllabus. Okay, both input and output are shared. Okay, for this case. Okay, for this case, your emitter is ground. Okay, now your base to emitter is your input, collector to emitter is your output. Okay, you have the multiplication of the gain here lah. Okay, we look at the example later. So common emitter, like I said, common emitter means emitter is ground. Okay, for this case, okay, so base to emitter is your input. Okay, this is base emitter, and collector to emitter is your output. Okay, so this is how your circuits looks like. Okay, in order to make it as a forward active, okay, forward active mode. So you connect base to emitter forward bias and collector to emitter reverse bias. Okay, this is how you connect. Right. Okay, so common emitter. Okay, since that you have input at base to emitter, and you also have output collected to emitter. Therefore, the input IV characteristic you also have to. Okay, the IV characteristic at input. So this is how it looks like. Okay, current IB versus voltage VBE. So current IV versus any voltage here. When you increase the voltage VBE, what happened to the current IV? So this is how it looks like. Okay, so when you increase, it will reach a knee voltage. Okay, the current will start increasing. But like I said, current IV is very, very small in the scale of microampere. Okay, so voltage drop if the transistor is made up of silicon. Okay, so the voltage drop here. Okay, the voltage drop across VBE here is 0.7 volt. Okay, 0.7 volt. Right. If let's say IB is greater or IB is 0, therefore VBE less than 0.7 volt. But if there is a value for IB, therefore VBE is greater than 0.7 volt. Okay, hence your transistor will turn on when the value VBE equal to 0.7 volt. Okay, when you have input IV characteristic. Okay, when you have input IV characteristic, you also have the output IV characteristic. So this is how it looks like, the output characteristic. So this is your collector current. So output is collector to emitter. Okay, therefore you have collector current and VCE current. Okay, so in here we can see that collector current is saturated. Okay, at any point of IB. Okay, because we know that from the equation, IC is equal to the beta over IB. Okay, as IB increase, okay, IC will also increase. Okay, in here, okay, you will have like three region. Okay, at this region we call it as a current. IC at this region is saturation current. Okay, current at this point, okay, is cut off region. Okay, whenever current fall in at the center here, okay, we call it as a Q point. We call it as a active region. Okay, during here, BJT will behave as an amplifier. Why? Because this is active region, okay, where the VBE is forward bias and BC is reverse bias. So for the common emitter region IV characteristic, for the saturation region, okay, both junctions are forward bias. All right. For the cutoff region, both junction are reverse bias, but this is the most important part. During active region, transistor will behave as an amplifier, where the base to emitter junction forward bias, base to collector junction reverse bias. Okay, IC will increase drastically, although there is a small change of IB. Why? This is because of beta value. Okay, all right. So these are the commons that you need to know. So the first one, so the second one here, and also the third one. So these three things that you need to know lah in order to analyze the BJT circuit, right? So in here, so when you have the input and output current, of course you can calculate the power dissipation. Okay, power out is equal to the IC versus times VCE at output region. Okay, so this is rarely asked, but of course you know power dissipation is equal to current times voltage output. Okay, so this is a summarization, okay, for the configuration when it is common emitter. Okay, common emitter means that emitter is grounded, so input it at base, output at collector. So I repeat in my slide again and again, I put the current relationship, okay, between collector and emitter. Okay, and therefore, I believe that you should have memorized lah this case. So alpha equal to IC over IE, and alpha is approximately equal to 1. So you can say that IC is approximately equal to IE, and IC is equal to beta IB. Finally, you will get this IE equal to beta plus 1 IV. Okay, you should have memorized these three things. Okay, 1, 2. Oh, sorry, 3. This one only. Okay. Okay. So we have 10 minutes. I think we can finish. We can continue this in the next lecture. How about that? You all okay?
Yes, Doctor.
Yeah.
Okay, great. Okay, so I think since the theory part same like PN junctions, you have to listen and listen. I think for, in the next class we'll do some calculation for BJT. Is that okay?
Yes.
All right. Okay,
that's
so
okay.
I'll stop there. All right. So I think I finished